Right now, light is hitting your eyes that left a galaxy 2.5 million years ago, when our ancestors were still chipping their first stone tools. That faint smudge in the night sky is the most distant thing you can see without a telescope. And it is racing toward us at 300,000 kilometers every single hour. This is why astronomers call Andromeda our future and our mirror at the same time. Because everything we think we know about our own galaxy, we learned by staring at this one. And what we found is far stranger than a simple neighbor drifting in the dark. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. You are looking at a galaxy so large that if it were bright enough to see fully with the naked eye, it would stretch across a piece of sky 6 times wider than the full moon. Think about that for a moment. The moon dominates the night. It is the brightest, largest object in our sky after the sun. And Andromeda, sitting at a staggering distance, would still cover an area 6 times broader if our eyes could only gather enough of its light. The reason we see only a tiny faint oval is not that Andromeda is small. It is that our eyes are weak, and the galaxy is unimaginably far away. The light you perceive is just the dense, bright core, the central bulge where stars crowd together so tightly that their combined glow can pierce 2.5 million light-years of empty space and still register on your retina. The rest of the galaxy, the vast spiral arms wheeling outward, the faint outer halo, all of it is there in the sky above you. You simply cannot see it. This is the first lesson Andromeda teaches us about scale. Our perception is a liar. What looks like a dim little patch is in fact a colossal island of stars, larger than our own Milky Way, holding within it a number of suns so great that the human mind has no honest way to picture it. For most of human history, no one knew what Andromeda was. Ancient astronomers who noticed it called it a little cloud. A Persian astronomer described it more than 1,000 years ago as a small, misty patch near the constellation we now call Andromeda. For centuries, that is all it was, a faint smudge among the fixed stars, easy to overlook, impossible to understand. Even when telescopes arrived, the mystery only deepened. Through early instruments, Andromeda looked like a fuzzy oval of light, and astronomers lumped it together with countless other fuzzy ovals scattered across the sky. They called these objects nebulae, from the Latin word for clouds. Most assumed they were clouds of gas floating somewhere within our own galaxy. The idea that the Milky Way might be just one galaxy among many had not yet taken hold. In fact, for a long time, the prevailing belief was that the Milky Way was the entire universe. Everything that existed, every star, every cloud, every point of light, was thought to be contained within our single, swirling collection of stars. The cosmos was the Milky Way, and the Milky Way was the cosmos. Andromeda was about to shatter that belief completely. The man who broke it open was an astronomer named Edwin Hubble, working in the 1920s with what was then the most powerful telescope on Earth, perched on a mountain in California. Hubble was studying that faint oval, and within it he found something extraordinary, a particular kind of star called a Cepheid variable. These stars are among the most useful objects in all of astronomy, because they pulse. They brighten and dim in a steady, predictable rhythm, and the speed of that rhythm reveals exactly how much light the star truly produces. Once you know how bright a star really is, and you measure how bright it appears from Earth, you can calculate its distance. It works like a candle in the dark. If you know how strong a flame is, you can judge how far away it must be by how dim it looks. When Hubble measured the Cepheids inside Andromeda, the answer he got was almost unbelievable. The stars were not thousands of light-years away. They were not tens of thousands of light-years away. They were so distant that they could not possibly be inside the Milky Way at all. Andromeda was not a cloud within our galaxy. It was a separate galaxy entirely, an island universe, drifting in the dark far beyond the edge of our own. In one stroke, the size of the known universe expanded beyond anything anyone had dared imagine. The Milky Way was no longer everything. It was just one galaxy among what we now know to be hundreds of billions, perhaps trillions. And Andromeda was the first one we ever recognized for what it truly was, a peer to our own, a great wheel of stars spinning in the void, separate and complete. That discovery did something deeper than just add a new object to the map. It changed humanity's place in the cosmos. Before Andromeda was understood, we could imagine ourselves at the center of a single, contained universe. After, we knew we were one galaxy among a multitude, adrift in a space so vast that our entire stellar home was reduced to a single point in an ocean without visible shores. So how far away is Andromeda, really? The number astronomers settle on is roughly 2.5 million light-years. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers every second. In a single year, that adds up to about 9.5 trillion kilometers. Now multiply that by 2.5 million. The number becomes so large that writing it out would fill the screen with zeros, and your mind would slide right off it. So instead, hold on to what the light itself tells you. When you look at Andromeda tonight, you are not seeing it as it is. You are seeing it as it was 2.5 million years ago. The light entering your eye began its journey before our species existed. It crossed the emptiness between galaxies for longer than humans have walked the Earth, and it arrives only now, at this exact moment, to land on you. Andromeda is a window into the deep past. Whatever is happening there right now, new stars igniting, old stars fading, worlds forming around distant suns, none of it has reached us yet. It will not reach us for 2.5 million more years. We are looking at a ghost of a galaxy, a portrait of how it appeared in an era we can barely comprehend. And yet, despite that enormous distance, Andromeda is considered close. It is, in fact, the nearest large galaxy to our own. That single sentence should reframe your entire sense of scale. The closest major galaxy to us is so far that its light takes 2.5 million years to arrive, and on the cosmic map, that counts as next door. Everything beyond Andromeda is farther still, stretching outward into distances that make even this number seem intimate by comparison. Now we come to the question that gives this journey its name. How big is Andromeda, truly? The galaxy spans roughly 200,000 light-years from one edge of its visible disk to the other. To cross it at the speed of light, the fastest anything can travel, you would need 200,000 years. A beam of light, leaving one rim of Andromeda, would have to travel for 2,000 centuries before reaching the opposite rim. Compare that to our own Milky Way, which measures somewhere between 100,000 and 120,000 light-years across. Andromeda is the larger of the two. It is the dominant galaxy in our local neighborhood, a sprawling spiral that outsizes our home. But the disk you can map with a telescope is not the whole story. Recent surveys have traced Andromeda's faint outer halo, a vast, thin cloud of stars and dark matter surrounding the bright spiral, and that halo reaches outward to an almost absurd extent. Measurements suggest it may stretch more than 1 million light-years across. The halo is so enormous that it nearly touches the halo of our own Milky Way. Let that settle. The two largest galaxies in our local group are so massive that their invisible outer envelopes are already brushing against each other across the gulf of intergalactic space. We are not as separate from Andromeda as the night sky makes it seem. In a very real sense, the edges of our two galaxies have already begun to meet. Inside that immense structure live the stars. And here the numbers leave the realm of ordinary imagination entirely. The Milky Way contains somewhere between 100 billion and 400 billion stars. Andromeda holds far more. Estimates put its population at around 1 trillion stars, 1 trillion suns. If you tried to count them one per second, never stopping to sleep or eat, it would take you more than 30,000 years just to finish counting the stars of this single galaxy. And every one of those stars is a sun. Some are small, dim, and cool, burning slowly for tens of billions of years. Others are giants, blazing blue and white, consuming themselves in a fraction of the time. Many of them, almost certainly, are circled by planets. If the worlds in our own galaxy are any guide, Andromeda may contain billions upon billions of planets, rocky worlds, gas giants, frozen moons, and perhaps places where conditions are gentle enough for something to stir into life. We cannot see those planets. We cannot even see most of those stars individually. At 2.5 million light-years, a single sun like ours would be hopelessly lost in the glow of its trillion neighbors. What we perceive as the smooth light of Andromeda is the merged radiance of an entire trillion-star civilization of suns, blended together by distance into a single, faint smear. To understand the true scale of Andromeda, you have to understand what a spiral galaxy actually is, because Andromeda is the grandest example we can study from the outside. We live inside the Milky Way, which means we can never see our own galaxy's full shape. We are trapped within it, like someone standing in the middle of a forest, trying to draw a map of the whole woodland from ground level. But Andromeda we can see from a distance, tilted at an angle that reveals its structure. By studying it, we learn what our own galaxy must look like. At the heart of Andromeda sits a dense, glowing central bulge, a tightly packed sphere of older stars, golden and red, crowded together near the galactic core. This is the part of Andromeda you can glimpse with the naked eye. Surrounding the bulge spreads the disk, a flattened plain of stars, gas, and dust, where the spiral arms wind outward in great sweeping curves. These arms are not solid structures. They are waves, density waves that move through the disk like ripples through water, triggering bursts of star formation as they pass. Where the arms are densest, gas clouds collapse and new stars ignite, which is why spiral arms shine so brightly. They are stellar nurseries, regions where suns are being born. Wrapped around all of this is the halo, the faint, spherical region of old stars, globular clusters, and the mysterious dark matter that holds the entire galaxy together. Andromeda's disk is studded with hundreds of globular clusters, dense balls, each containing hundreds of thousands of ancient stars. Our Milky Way has fewer. Andromeda, true to its larger scale, hosts an even richer collection of these ancient stellar cities. Every element of this structure works on a scale that dwarfs human experience. The distances between stars in the disk are measured in light-years. The clouds of gas where new suns form span dozens or hundreds of light-years on their own. The entire system spins, slowly and majestically, with the inner regions completing a rotation faster than the outer edges, all of it bound together by gravity across the abyss. And at the very center of it all lies something that should not be possible: a supermassive black hole. At the core of Andromeda, hidden within that bright central bulge, sits a black hole with a mass tens of millions of times greater than our Sun. Some measurements suggest its mass reaches well over 100 million times the mass of our star, making it considerably larger than the supermassive black hole at the heart of the Milky Way. A black hole is a region where gravity has become so overwhelming that nothing can escape it, not matter, not light, nothing. It is a place where the fabric of space itself is pulled into an endless pit. The boundary around it, the point of no return, is called the event horizon. Cross it, and there is no coming back. For Andromeda's central black hole, that boundary alone is larger than our entire solar system. The stars near the galactic core orbit this monster at tremendous speeds, whipped around by its colossal gravity. By measuring how fast those stars move, astronomers can weigh the invisible object pulling on them, and the answer is staggering. A single point in space holding the mass of 100 million suns, compressed into a region from which not even light can flee. Strangely, Andromeda's core holds another mystery. When astronomers looked closely at the very center, they found not one bright knot of stars, but what appeared to be a double nucleus, two peaks of light flanking the black hole. The explanation seems to be that the stars near the center are arranged in an eccentric disk, an elongated ring where they linger longer at the far end of their orbits, piling up to create the illusion of a second nucleus. It is a reminder that even the parts of Andromeda we can study in detail still hold puzzles we are only beginning to unravel. Now, having established just how vast Andromeda is, we arrive at the part of this story that transforms it from a distant curiosity into something deeply personal. Andromeda is coming. This galaxy, sitting 2.5 million light-years away, is not drifting peacefully alongside us. It is moving toward the Milky Way, falling through space under the pull of gravity, approaching at a speed of roughly 300,000 kilometers every hour. At that velocity, Andromeda is closing the gap between us by an immense distance every single day, every single year, relentlessly. Most galaxies in the universe are moving away from us. The universe is expanding, carrying galaxies apart, stretching the space between them so that the vast majority of distant galaxies recede from our view, their light shifted toward the red end of the spectrum as they flee. But Andromeda is different. Andromeda's light is shifted toward the blue. It is one of the few large galaxies in the entire sky that is approaching rather than retreating. Gravity has overpowered the expansion of the universe in our little corner of the cosmos. The Milky Way and Andromeda are bound to each other, two giants locked in a slow gravitational embrace, falling inexorably toward a meeting that has been building for billions of years. When will they collide? The current estimates suggest the two galaxies will begin to merge in roughly 4 to 4.5 billion years. That is an almost incomprehensible span of time, longer than the Earth has currently existed, stretching far into a future none of us will witness. By the time Andromeda arrives, our sun will be nearing the end of its own life, swelling into a red giant. But the collision itself, when it finally comes, will be one of the most spectacular events imaginable. And here is where intuition fails completely. When you hear the word collision, you picture catastrophe, stars smashing into stars, worlds shattering, a violent crush of matter. The reality is almost the opposite. Galaxies are mostly empty space. The distances between individual stars are so enormous that when two galaxies pass through each other, the stars almost never touch. Picture two swarms of bees, each bee separated from the next by kilometers of open air, drifting through one another. The swarms merge, but the individual bees sail past each other untouched. That is what happens when galaxies collide. The chance of our sun directly striking an Andromeda star is so small as to be almost zero. What actually happens is a vast, slow gravitational dance. As the two galaxies interpenetrate, their mutual gravity tears at their shapes. The elegant spiral arms are pulled into long streamers of stars, flung outward into the dark in great glowing tides. Gas clouds, however, do collide. Unlike stars, the diffuse clouds of gas spread throughout each galaxy are large enough to slam into one another, and when they do, they compress violently, triggering an explosion of new star formation. The merging galaxies light up with the birth of countless new suns, a burst of brilliant young stars blazing into existence as the collision stirs the cosmic gas like a spoon through a pot. This first pass will not be the end. The two galaxies will swing past each other, pulled back by gravity, and return for a second encounter, and perhaps a third. Over hundreds of millions of years, they will dance closer and closer, their structures unraveling, until finally they lose their separate identities entirely and settle into a single, vastly larger galaxy. The two supermassive black holes at their centers will spiral toward one another, eventually merging into one truly gigantic black hole at the heart of the new combined galaxy. The spirals will be gone. In their place will rise an enormous elliptical galaxy, a smooth, featureless ball of stars with no arms, no disk, just a great rounded swarm of suns. Astronomers have given this future galaxy a nickname, blending the names of its parents. They call it Milky. If any descendants of life on Earth survive to witness it, they will look up at a night sky transformed. For a stretch of time, spanning hundreds of millions of years, the sky will be filled with the spectacle of the merger, vast arcs of stars, brilliant clusters of newborn suns, the two galactic cores blazing as they approach each other. It would be the most magnificent sight any conscious being could ever behold, a slow-motion fireworks display playing out across the entire dome of the heavens. But what about us? What about the Sun, the Earth, our solar system? When the merger happens, where will we end up? The honest answer is that no one can predict the exact fate of any single star in such a chaotic gravitational event. Our solar system might be flung into the outer reaches of the new galaxy, cast out into a long, lonely orbit far from the crowded center. Or it might be drawn inward, closer to the galactic core. It might even be ejected entirely, hurled out into intergalactic space to wander alone forever. What is nearly certain is that the Earth itself, the physical planet, will not be destroyed by the collision. The stars are too far apart for direct impacts. But by the time Andromeda arrives, the Earth as a living world will already be long gone, scorched by an aging, swelling sun, billions of years before Andromeda ever touches us. The collision will be a spectacle for whatever the cosmos holds at that distant time, but it will unfold over an empty, transformed Earth if the planet endures at all. This is the strange intimacy of Andromeda. It is unfathomably far away, yet bound to us by gravity. It is a thing of the deep past, since its light is millions of years old, yet it is also a thing of the deep future, since it represents the eventual fate of our own galaxy. To look at Andromeda is to look at where the Milky Way is heading. Let us return to the matter of distance, because the scale of Andromeda only makes sense when you grasp the scale of the emptiness around it. The space between Andromeda and the Milky Way is not merely large, it is almost perfectly empty. If you were to travel from one galaxy to the other, you would spend the overwhelming majority of your journey in absolute void, vast stretches of nothing, with only the faintest scattering of hydrogen atoms drifting through the dark, and the rare lonely star cast out from its home galaxy long ago. For 2.5 million light-years, there is essentially nothing, and this emptiness is not unusual. It is the normal state of the universe. Galaxies are tiny bright islands separated by oceans of nothing. The matter we care about, stars, planets, the stuff of life, clusters together into these glowing islands, while the space between them yawns open, dark, and unimaginably wide. Andromeda and the Milky Way are members of a small cluster of galaxies bound together by gravity, called the Local Group. This group contains more than 50 galaxies, but it is dominated by just two giants, the Milky Way and Andromeda. Everything else is small, by comparison. Dwarf galaxies, orbiting the two great spirals like moths circling a pair of lanterns. Andromeda has its own retinue of these companions. Two of the most prominent are small elliptical galaxies that hang close beside it, visible in the same telescopic view, gravitationally bound to their giant host. These dwarf companions orbit Andromeda, and over cosmic time, the great spiral devours them, tearing them apart and absorbing their stars into its own halo. This is how galaxies grow. They are cannibals. Andromeda did not begin as the trillion-star giant we see today. It grew over billions of years by swallowing smaller galaxies, one after another, ripping them apart and weaving their stars into its own structure. Astronomers have found evidence of these ancient meals written into Andromeda's halo. Vast streams of stars, the shredded remains of galaxies consumed long ago, still tracing ghostly arcs through space. These stellar streams are like the ripples left on a pond after a stone sinks beneath the surface, the last visible trace of galaxies that no longer exist as separate things. Our own Milky Way has done the same. We too have consumed smaller galaxies, and we are doing so even now, with the shredded remnants of devoured dwarfs spread through our own halo. The two largest predators in the local group, Andromeda and the Milky Way, have spent billions of years growing fat on their smaller neighbors, and now, at last, they are turning toward each other. When you consider Andromeda's history of growth, its true scale becomes even more impressive. The trillion stars did not all form in one place. Many of them were born in other, smaller galaxies that Andromeda later swallowed. The galaxy you see is an assembly, a patchwork stitched together over billions of years from the bodies of its victims. Its outer halo, in particular, is a graveyard of consumed galaxies, layered like the rings of an ancient tree, each layer recording a meal from a different epoch of cosmic history. By studying these layers, astronomers can read Andromeda's biography, when it grew most rapidly, when it merged with its largest companions, how its structure was shaped by collision after collision. It turns out Andromeda has had a far more violent history than our own Milky Way. The Milky Way appears to have had a relatively calm life, with no truly enormous mergers in recent cosmic times. Andromeda, by contrast, seems to have endured at least one major collision in its past, a great merger that left its halo richer and more disturbed than our own. This is part of why Andromeda is larger and holds more stars. It has been the more aggressive of the two galaxies, the one that grew through dramatic violence rather than quiet accumulation. And it is this same hunger, this same gravitational appetite, that now draws it toward us. The encounter 4 billion years from now will be Andromeda's grandest meal of all, and ours. The Milky Way and Andromeda are roughly matched in size, so neither will simply swallow the other. Instead, they will merge as equals, two titans combining into something greater than either could have become alone. Let us turn now to how astronomers measure all of this, because the methods themselves reveal the scale of the challenge. When Hubble first measured Andromeda's distance using Cepheid variable stars, he established a technique that astronomers still use today. These pulsing stars remain one of the most reliable cosmic yardsticks we have. But measuring a single galaxy 2.5 million light-years away pushes even our best instruments to their limits. To resolve individual stars in Andromeda, to pick out the faint pulsing Cepheids and measure their rhythms, requires telescopes of extraordinary power, instruments capable of separating one tiny point of light from the blended glow of a trillion neighbors. Space telescopes, lifted above the blurring atmosphere of Earth, have given us our sharpest views. With them, astronomers have produced images of Andromeda containing more than 100 million individual stars, the largest, most detailed portraits of any galaxy beyond our own ever assembled. To capture such an image requires stitching together hundreds of separate photographs, each one a small tile, combined into a single, colossal mosaic. And even with 100 million stars resolved, that represents only a fraction of Andromeda's total population. The galaxy holds 1 trillion suns. 100 million is 1/10 of the whole. We are seeing only the brightest, the nearest, the easiest to pick out, and still the image is so vast and detailed that exploring it fully would take a lifetime. This is the recurring theme of Andromeda. Everything about it is larger than our instruments, larger than our imagination, larger than the words we have to describe it. We measure its distance and the numbers overwhelm us. We count its stars and lose track in the billions. We map its halo and find it brushing against our own. We trace its history and uncover a violent saga of consumed galaxies stretching back billions of years. And through all of it, the galaxy itself remains just a faint oval to the naked eye, a smudge of light that most people glance past without a second thought. Consider what it means to truly understand the speed of light in the context of Andromeda. Light is the fastest thing in existence. Nothing can travel faster. In 1 second, light crosses 300,000 kilometers, enough to circle the Earth more than 7 times. In 1 second. From the Earth to the Moon takes light only a little over 1 second. From the Sun to the Earth takes about 8 minutes. The light that warms your face left the surface of the Sun 8 minutes ago. To cross our entire solar system, from the Sun to the most distant reaches, light needs many hours. To reach the nearest star beyond our Sun, light needs about 4 years. And to cross from Andromeda to here, that same light, the fastest thing in the universe, needs 2.5 million years. Hold these numbers side by side, and the true gulf opens before you. 1 second to circle the Earth. 8 minutes to reach us from the Sun. 2.5 million years to arrive from Andromeda. The fastest thing that exists, traveling without rest, takes longer to reach us from our nearest galactic neighbor than our entire species has existed. That is the scale of Andromeda. That is the scale of the space between us. And yet, on the map of the universe as a whole, this enormous distance is microscopic. The observable universe stretches outward for tens of billions of light years in every direction. Within it lie hundreds of billions of galaxies, perhaps trillions, scattered across distances that make the gap to Andromeda seem like the width of a single step. If the entire observable universe were shrunk down to the size of a city, the distance to Andromeda would be smaller than the thickness of a single sheet of paper. Andromeda is our closest large neighbor, and even it is unfathomably far. Everything else is farther still. This is the humbling truth that Andromeda first taught humanity a century ago, and it has only grown more profound with every passing decade. We are not the center of the universe. We are not even a particularly large island within it. We are one galaxy, beside one neighbor, within one small group, in one corner of a cosmos so vast that our most powerful telescopes have only begun to chart its shores. But there is wonder in this smallness, not just terror. Consider that from this tiny vantage point, a single planet, orbiting a single ordinary star, in the outskirts of a single galaxy, intelligent beings looked up, noticed a faint smudge of light, and slowly, painstakingly, figured out what it was. We measured its distance. We counted its stars. We weighed its central black hole. We traced its history of devoured galaxies. We predicted its collision with our own home, 4 billion years into the future. All of this, from a faint oval that ancient people dismissed as a little cloud. That is the other side of Andromeda's lesson. The universe is unimaginably vast, and we are unimaginably small. But the mind is capable of reaching across that vastness, of comprehending distances and timescales that dwarf our brief lives, of standing on one tiny world and understanding a galaxy 2.5 million light-years away. Let us linger on what Andromeda will look like as it approaches over the coming billions of years, because the view from Earth, or from whatever inherits the Earth's place, will change in slow, magnificent stages. Today, Andromeda is a faint oval, visible only on dark nights to those who know where to look. But as it draws nearer across the eons, it will grow larger and brighter in our sky. In 1 billion years, it will be noticeably bigger than it is now, a luminous patch impossible to miss. In 2 billion years, it will dominate one corner of the heavens, its spiral arms perhaps just becoming visible as distinct features even to the unaided eye. In 3 billion years, it will loom enormous, a great wheel of stars hanging in the sky, brighter than anything except the sun and moon. And as the two galaxies begin to merge, the night sky will erupt into a spectacle beyond any sunset, the tangled spiral arms of both galaxies stretched into glowing arcs, the brilliant flares of newborn stars igniting where the gas clouds collide, the two galactic cores blazing as they spiral toward their union. No one alive today will see it. No one for billions of years will see it. But it is coming, written into the gravity of the cosmos, as certain as the dawn. The smudge in our sky tonight is a slow-motion arrival, a guest that has been falling toward us since before the dinosaurs, and will keep falling long after every trace of our civilization has turned to dust. Think about the chain of light that connects you to Andromeda right now. The photons striking your eye, if you were to look up tonight, began their journey 2.5 million years ago. They crossed the empty void between galaxies for a span of time longer than human history, longer than human civilization, longer than the existence of our species. They passed through the dark, untouched, for millions of years, carrying with them an image of a galaxy as it was in a vanished age. And then, tonight, after that impossibly long journey, they end, absorbed by the cells of your eye, registered by your brain, becoming a faint patch of light in your perception. You are the destination of a journey that began before humanity. You are the end point of light that is older than your species. When you look at Andromeda, you complete a voyage millions of years in the making. There is something profound in that connection. Across an ocean of emptiness, across an abyss of time, a galaxy reaches out and touches you with its ancient light, and for a moment, the two of you, the trillion-star giant and the single fragile observer, are linked by nothing more than a thread of photons that has been traveling since before you, or anyone like you, existed. This is what scale truly means. Not just big numbers, not just distances too large to picture, but the realization that the universe operates on a stage so vast that light itself becomes a relic by the time it reaches us, that galaxies fall toward each other over billions of years, that the faintest smudge in the sky is, in truth, a colossal world of 1 trillion suns falling slowly toward a collision with our own. Andromeda is our neighbor, our future, our mirror, and our messenger from the deep past. It taught us that we are not alone in the universe of galaxies, that the Milky Way is one of countless islands of light. It showed us our own structure by letting us see from the outside what we can never see from within. It carries within it the fate that awaits our own galaxy, the merger, the loss of the spiral form, the birth of a vast new elliptical city of stars. And it does all of this while appearing to our eyes as nothing more than a faint, dim oval, easily overlooked, almost forgotten. The next time you find yourself under a truly dark sky, away from the glow of cities, take a moment to find it. Look toward the constellation that bears its name, and search for that small misty patch that ancient astronomers called a little cloud. When you find it, remember what you are actually seeing. You are looking at a galaxy 200,000 light-years wide, holding 1 trillion stars, surrounded by a halo that reaches across 1 million light-years toward your own home. You are seeing light that left before your species existed. You are watching a giant falling slowly toward you across the dark, destined to merge with everything you have ever known billions of years from now. You are gazing at the true scale of Andromeda, and through it, at the true scale of the universe itself, and your own astonishing, fragile, wondrous place within it. That faint smudge is not small. It only looks that way from here. And the fact that you can stand on one tiny world and understand all of this, that you can hold 1 trillion stars in your mind, measure a distance of millions of light years, and predict a collision 4 billion years away, that may be the most remarkable thing of all. The universe is vast beyond comprehension. Andromeda is one proof of that, drifting in our sky every clear night. But the mind that looks up and understands it, that, too, is part of the cosmos coming to know itself. There is more to Andromeda's story, and it is worth slowing down to consider the individual pieces that make up this colossal galaxy, because the scale of the whole is built from the scale of its parts. Begin with a single star within Andromeda, one of the brightest, most luminous suns the galaxy contains. There are stars in Andromeda so vast that if you placed one where our sun sits, it would swallow the orbits of the inner planets entirely. These are the blue supergiants and red supergiants, stars dozens of times more massive than our sun, blazing with the brilliance of hundreds of thousands of suns combined. They are the lighthouses of the galaxy, the points of light that astronomers can pick out individually, even across 2.5 million light-years. A star like our sun, by contrast, is invisible at that distance. Our sun is a modest yellow star, perfectly ordinary, and from Andromeda it would be utterly lost. If beings in Andromeda were to look toward the Milky Way, they would see our galaxy as we see theirs, a faint oval smudge of blended light, with no individual sun standing out, certainly not ours. They could not see our sun. They could not see the Earth. They could not see us, and we cannot see them, if they exist. The two galaxies regard each other across the void as featureless ovals. Each one, 1 trillion or 100 billion stars, merged into a single soft glow, each one blind to the individual worlds that might harbor life within the other. This is the loneliness built into the scale of the cosmos. Even our nearest large neighbor is so far that no detail of life within it could ever reach us, and no detail of life within ours could ever reach it. We are islands not only of matter, but of knowledge, sealed off from one another by distances that light itself struggles to cross. Now consider the gas and dust between the stars of Andromeda, because the empty-looking space within a galaxy is not truly empty. Threaded through Andromeda's spiral arms are vast clouds of gas, mostly hydrogen, the simplest and most abundant element in the universe, along with fine grains of cosmic dust. These clouds are the raw material of stars. When a cloud grows dense enough, gravity takes hold and pulls it inward, compressing the gas until, at the center, the pressure and temperature climb high enough to ignite the fire of fusion. A new star is born. Andromeda is still forming stars, though more slowly than it once did. In its youth, billions of years ago, the galaxy blazed with star formation, churning out new suns at a furious pace. Today, that pace has slowed. Andromeda is a more mature galaxy than the Milky Way in some respects. Its star-forming gas partly depleted, its great burst of creation already past its peak. But the clouds remain, and within them, new stars continue to flicker into existence, just at a gentler rhythm. The dust in those clouds matters too, in a way that connects directly to us. The fine grains drifting between Andromeda's stars are made of heavier elements: carbon, silicon, iron, oxygen, elements that did not exist when the universe began. In the beginning, after the great expansion that birthed the cosmos, there was almost nothing but hydrogen and helium. Every heavier element, everything that makes up rock and water and living flesh, was forged inside stars. Stars are the factories of the elements. In their cores, through fusion, they build heavier atoms from lighter ones. And when massive stars reach the end of their lives and explode, they scatter those newly forged elements across space. That enriched material then becomes part of new clouds, new stars, new planets. Andromeda, like the Milky Way, has been running this cycle for billions of years, building elements, scattering them, building worlds from the debris. Every rocky planet in Andromeda, if such planets exist, is made of star stuff, cooked in the hearts of suns that lived and ended long ago. The same is true of you. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged inside stars, scattered by their final explosions, and gathered into the cloud that became our sun and its planets. You are, quite literally, made of the same processes that built Andromeda. The galaxy and the sky and the body reading these words share a common origin in the fusion fires of ancient stars. Across 2.5 million light-years, you and Andromeda are kin. Let us return to the question of the supermassive black hole at Andromeda's center, because it deserves deeper exploration. Every large galaxy, as far as we can tell, harbors a supermassive black hole at its core. The Milky Way has one, a black hole called Sagittarius A, with a mass around 4 million times that of our Sun. Andromeda's central black hole is far larger, weighing in at well over 100 million solar masses by some estimates. How does a black hole grow so monstrous? It feeds. Over billions of years, gas, dust, and even entire stars that wander too close are pulled inward, swallowed forever beyond the event horizon. As material spirals toward the black hole, it heats to tremendous temperatures, glowing with intense radiation before it vanishes. In the distant past, when galaxies were young and rich with gas, these central black holes fed voraciously, blazing as some of the brightest objects in the entire universe. Today, both Andromeda's black hole and our own are relatively quiet, having consumed much of the easy material around them. But the connection between a galaxy and its central black hole runs deep. Astronomers have discovered that the mass of a galaxy's central black hole is closely related to the properties of the galaxy as a whole, as if the black hole and the galaxy grew up, together, shaping each other across cosmic time. When Andromeda and the Milky Way finally merge, their two central black holes will be drawn toward one another, sinking to the center of the new combined galaxy. There they will orbit each other in an ever-tightening spiral, until at last they merge into a single, even more massive black hole. That final merger will release a burst of gravitational waves, ripples in the fabric of space itself, radiating outward across the universe, a faint tremor in the cosmos marking the union of two galactic hearts. The scale of such an event is almost beyond comprehension. Two objects, each containing the mass of millions or hundreds of millions of suns, spiraling together and combining, sending shudders through the very geometry of space. This is the kind of event that Andromeda's future holds, and the Milky Way's with it. Let us also consider the dark matter that holds Andromeda together, because without it, the galaxy could not exist as we see it. When astronomers measure how fast the stars in Andromeda orbit the galactic center, they find something puzzling. The stars at the outer edges move far too fast. If the only matter in Andromeda were the matter we can see, the stars, the gas, the dust, then the outer stars should fly off into space, unable to be held by such weak gravity. But they do not fly off. They orbit steadily, held in place by far more gravity than the visible matter can account for. The conclusion is inescapable. There must be a great deal of matter in Andromeda that we cannot see. Matter that gives off no light, emits no radiation, and reveals itself only through its gravity. This is dark matter, one of the deepest mysteries in all of science. We do not know what it is made of. We have never directly detected a single particle of it, and yet it appears to make up the overwhelming majority of the mass in galaxies like Andromeda, perhaps 5 or 6 times as much as all the visible stars and gas combined. The bright, glowing spiral you see is merely the visible tip of a far larger structure, a vast invisible halo of dark matter, extending far beyond the stars, enveloping the entire galaxy in an unseen cocoon. That dark matter halo is what reaches outward across 1,000,000 light-years, brushing against the dark matter halo of our own Milky Way. When we say the two galaxies' halos are already touching, it is largely their dark matter halos. We mean the invisible scaffolding that gives each galaxy most of its mass. So the true Andromeda is not just the trillion stars we can imagine. It is those stars, plus an even greater quantity of mysterious, invisible matter, all bound together into a single immense gravitational structure that dwarfs the visible galaxy several times over. When you look at the faint oval in the sky, you are seeing only a fraction of what is truly there. The rest is dark, present, powerful, and utterly hidden. This is humbling in a different way. It means that even the colossal scale of Andromeda's visible self is only a glimpse of the whole. The galaxy is larger, heavier, and more mysterious than its light alone can ever tell us. Now let us think carefully about time, because Andromeda forces us to confront timescales that lie far outside ordinary human experience. The light reaching us tonight is 2.5 million years old. The collision with the Milky Way lies 4 billion years in the future. The stars within Andromeda have lifespans ranging from a few million years for the largest to many billions of years for the smallest. The galaxy itself formed billions of years ago, in the early ages of the universe, and has been evolving ever since. To Andromeda, a human lifetime is less than the blink of an eye. Less than that, it is nothing at all, a duration too brief to register against the slow turning of a galaxy. Andromeda completes a single rotation roughly every few 100 million years. In the entire span of human civilization, the rise of cities, the invention of writing, every empire that has ever existed and fallen, Andromeda has not completed even 1,000th of a single turn. The galaxy is, for all practical purposes, frozen from our perspective. The image we see tonight is essentially identical to the image our distant ancestors would have seen, and essentially identical to the image our distant descendants will see. On human timescales, Andromeda does not change. It simply hangs there, eternal and unmoving, a fixed feature of the sky. And yet, on cosmic timescales, it is in constant, dramatic motion, rotating, falling toward us, consuming smaller galaxies, forming new stars, all of it unfolding so slowly that no human will ever perceive a single moment of change. This is the strange duality of the cosmos. What appears utterly static to us is in fact churning with activity, just at a tempo so vast that our brief lives cannot capture even a single frame of the motion. To truly see Andromeda change, you would need to watch it not for a lifetime, not for 1,000 lifetimes, but for millions of years. Only then would the faint oval begin to visibly grow, brighten, and at last transform as it merges with our home. We are like fireflies, trying to comprehend the slow growth of a mountain. The mountain is rising, the continents are drifting, but within the brief flash of our existence, everything appears frozen in stone. Consider, too, what Andromeda tells us about the broader structure of the universe. Galaxies are not scattered randomly through space. They gather into groups, and groups gather into clusters, and clusters gather into superclusters, all connected by vast filaments of galaxies stretching across hundreds of millions of light-years. This grand architecture is called the cosmic web, an immense network of galaxy-filled strands surrounding enormous empty voids. Like a three-dimensional spider's web spun across the entire universe. Andromeda and the Milky Way, together with their small companions, form the local group, a single modest knot in this vast cosmic web. Our local group is itself drifting toward a much larger gathering of galaxies, drawn by the immense gravity of distant superclusters. So Andromeda is not only falling toward us, the two of us together are falling towards something far larger. Still, swept along on a current of gravity that flows through the cosmic web. Everything is in motion. Everything is being pulled. The galaxies stream along the filaments of the cosmic web like water flowing downhill, gathering into ever larger structures, while the empty voids between the filaments grow emptier and wider with the expansion of the universe. Andromeda's journey toward us is one small thread in this immense tapestry of cosmic motion, a single act in a drama playing out across the entire universe, on scales of distance and time that reduce our galaxy and our neighbor galaxy to mere specks in an unimaginably larger design. And still, even knowing all of this, the smudge in the sky remains a smudge. That is perhaps the most astonishing thing about Andromeda. All of this immensity, the trillion stars, the supermassive black hole, the invisible dark matter halo reaching across 1,000,000 light-years, the violent history of devoured galaxies, the future collision, the place within the cosmic web, all of it is contained within that one faint patch of light that you could cover with the tip of your finger held at arm's length. The universe hides its grandest structures in plain sight, dimmed by distance, reduced to faint glimmers that most people will never notice, and fewer still will ever understand. But you understand now. You know that the faint oval is a galaxy larger than our own. You know it holds 1,000,000,000,000 suns. You know it is rushing toward us, destined to merge with the Milky Way and transform our sky into a spectacle of cosmic proportions. You know that the light you see is older than humanity, and that the galaxy is bound to us by gravity across an ocean of emptiness, 2.5 million light-years wide. Before we go deeper into the parts of Andromeda, it is worth pausing on the sheer variety of stars contained within it. Because 1,000,000,000,000 suns is not 1,000,000,000,000 copies of the same thing. Stars come in an enormous range of sizes, colors, temperatures, and lifespans, and Andromeda holds examples of every kind. There are red dwarfs, small, cool, dim stars that burn their fuel so slowly they can shine for tens of billions of years, far longer than the current age of the universe. These are the most common stars of all, and Andromeda surely contains them in the hundreds of billions. They are so faint that even up close they would seem dim, but their patience is extraordinary. They will outlast nearly every other kind of star, glowing quietly long after the brilliant giants have burned themselves out. Then, there are stars like our Sun, yellow stars of middling size, burning steadily for roughly 10 billion years, bright enough to warm a system of planets, but modest compared to the true giants. And there are the giants themselves, blue and white stars many times the mass of our Sun, blazing with ferocious intensity, consuming their fuel so rapidly that they live only a few million years before exhausting themselves. These massive stars are the ones that end their lives in tremendous explosions, scattering the heavy elements they forged across the surrounding space. Andromeda has witnessed countless such explosions over its long history, brilliant flashes that briefly outshine entire regions of the galaxy, marking the violent ends of its most massive stars. When one of these explosions occurs, it can shine, for a short time, as brightly as a billion ordinary stars combined. Astronomers have observed such explosions in Andromeda, sudden points of light flaring up within the distant galaxy, each one the final moment of a massive sun. The light from those explosions, like all of Andromeda's light, takes 2.5 million years to reach us, meaning the explosions we observe today actually happened in an unimaginably distant past, their light only now completing its long journey to our telescopes. Between these extremes lie stars of every intermediate kind. In every stage of life, young stars freshly ignited within the galaxy's gas clouds, middle-aged stars burning steadily, old stars swelling into red giants as they near their ends, and the faded remnants of stars that have already died. Those remnants take their own remarkable forms. When a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind a small, dense, glowing core called a white dwarf, an object roughly the size of the Earth but containing much of the mass of a star, so dense that a spoonful of its material would weigh tons. Andromeda is littered with these stellar corpses, the cooling embers of suns that lived and died long ago. When a more massive star explodes, it can leave behind an even stranger remnant, a neutron star, an object so dense that the mass of an entire sun is crushed into a sphere only kilometers across. A neutron star is so compact that a spoonful of its material would weigh as much as a mountain. And the most massive stars of all, when they collapse, leave behind black holes, regions where gravity has become so overwhelming that nothing, not even light, can escape. Andromeda contains all of these white dwarfs, neutron stars, and stellar black holes scattered throughout its disk and halo, the accumulated remains of billions of years of stellar life and death. So when we say Andromeda holds 1 trillion stars, we are describing not a uniform collection, but a vast, diverse population, a galaxy-spanning census of every kind of star, in every stage of existence, from the faintest red dwarf to the most brilliant supergiant, from newborn suns to ancient stellar corpses. This diversity is part of what makes the scale of Andromeda so staggering. It is not just a large number of identical objects. It is 1 trillion distinct suns, each with its own mass, its own brightness, its own lifespan, its own story, and very likely, for many of them, its own system of planets. To truly grasp Andromeda is to understand that within that faint smudge of light lies a population of stars more numerous and more varied than anything the human mind can hold. Now consider the spaces between those stars, because the emptiness within Andromeda is as much a part of its scale as the stars themselves. If you could stand on a planet orbiting a star somewhere in Andromeda's disk, you would not be surrounded by a crowd of nearby suns blazing in all directions. The stars, despite their enormous number, are spread across such vast distances that each one is separated from its neighbors by light years of empty space. Even in the relatively crowded regions of a galaxy's disk, the distance between one star and the next is typically several light years. This means that the night sky of a planet in Andromeda would look much like our own, scattered points of light against a black background, with vast darkness between them. The galaxy looks like a solid glowing disk from a distance, only because we are seeing the combined light of 1 trillion stars blended together across 2.5 million light-years. Up close, it would be mostly empty space, with stars as isolated islands, separated by enormous gulfs. This is why, when galaxies collide, their stars almost never strike one another. The spaces between stars are so vast that even two galaxies passing through each other rarely bring individual suns into contact. The emptiness within Andromeda is the same emptiness that fills our own galaxy, the same emptiness that fills the universe. Matter, for all its apparent abundance when we look at a glowing galaxy, is in truth spread incredibly thin across the cosmos, concentrated into tiny bright points separated by overwhelming darkness. Andromeda, that radiant wheel of 1 trillion suns, is mostly nothing at all. The light deceives us into seeing a solid object, but the reality is a vast, sparse scattering of stars across an enormous volume of empty space. This is yet another lesson in scale, that even the densest, brightest structures in the universe are, on close inspection, mostly void. Let us linger on the question that haunts every contemplation of a galaxy with 1 trillion suns, the question of whether anyone is looking back. Among Andromeda's trillion stars, how many might host planets? If our own galaxy is any guide, the answer is staggering. In the Milky Way, astronomers have found that planets are common, that most stars host worlds of some kind, and that small rocky planets like the Earth are abundant. If the same holds true for Andromeda, then the galaxy contains not millions, not billions, but likely hundreds of billions of planets. Among those hundreds of billions of worlds, some fraction would lie in the gentle zone around their star where liquid water could exist. The region neither too hot nor too cold, where the conditions for life as we understand it might be met. Even if only a tiny fraction of Andromeda's planets are suitable for life, a tiny fraction of hundreds of billions is still an enormous number. The mathematics of such vast quantities makes it seem almost inevitable that life would have arisen somewhere among Andromeda's stars. And yet, we cannot know. We have no way to detect life across 2.5 million light-years. We cannot see Andromeda's planets at all. They are far too small and faint, lost utterly in the glare of their suns at such a distance. We cannot detect any signal that might be passing between Andromeda's stars. The galaxy keeps its secrets completely. If there are civilizations among those trillion suns, beings who look up at their own night sky, who gaze toward the faint smudge of the Milky Way and wonder, as we do, whether anyone is out there, we would never know. And they would never know us. The distance is an unbreachable wall. Even if an advanced civilization in Andromeda were broadcasting signals at this very moment, those signals would take 2.5 million years to reach us. And by the time they arrived, the civilization that sent them might be long vanished. Conversely, any signal we sent toward Andromeda would not arrive for 2.5 million years, long after our own civilization, in all likelihood, had passed into history. The galaxies regard each other across a gulf that no message could meaningfully cross within the lifetime of any civilization. This is the great silence imposed by cosmic scale. The universe may be teeming with life, and yet each island of life remains isolated. separated from the others by distances and timescales that make contact all but impossible. Andromeda, with its trillion suns and its likely billions of worlds, may be home to wonders beyond imagining, and we will never know any of them. We can only look at the faint light, knowing that within it lies a galaxy that might be as full of life and thought and civilization as our own, and accept that the gulf between us is one that nothing can cross. There is a strange beauty in that. Two galaxies, each potentially full of conscious beings, drifting toward each other across the dark, neither able to know the other, until at last, 4 billion years from now, they merge into one, their stars mingling, their worlds brought into a single galaxy at last. If any life survives in either galaxy until that distant time, the merger would, in a sense, finally bring the two populations together, not through travel or signal, but through the slow gravitational dance of the galaxies themselves. It is the only way the two could ever truly meet. Now consider what the sky of a planet within Andromeda might look like, because it would be, in many ways, much like our own. A being standing on a world deep within Andromeda's disk would look up and see a sky full of stars. They're galaxy stars, scattered across the heavens, much as the Milky Way's stars are scattered across ours. They would see a luminous band arching across their sky, the combined glow of their galaxy's disk, seen edge-on from within, just as we see the band of the Milky Way arching across our own night. They would have their own constellations, their own patterns traced among the stars, their own myths and stories perhaps written across the sky. And if they looked in the right direction, on a dark enough night, they might see a faint smudge of light low in their sky, a small misty oval that their ancient astronomers might have called a little cloud. That smudge would be the Milky Way. Our galaxy, seen from Andromeda, would appear exactly as Andromeda appears to us, a faint, dim oval, easily overlooked. Its trillion, or 100 billion, stars merged into a single soft glow by the immensity of the distance. If those beings developed astronomy as we did, they might one day resolve that smudge into individual stars and realize, as Hubble did, that it was a separate galaxy lying far beyond their own. They might measure its distance and find it to be 2.5 million light-years away. They might even discover that it was approaching, falling toward their galaxy under the pull of gravity, destined to collide in 4 billion years. In other words, the beings of Andromeda, if they exist, would make the very same discoveries about the Milky Way that we have made about Andromeda. They would see us as their nearest great neighbor, their future companion, their mirror in the sky. The symmetry is perfect. Two galaxies, each studying the other, each making the same discoveries, each unable to communicate, each falling toward the other across the void. It is a kind of cosmic poetry, a relationship of perfect mutual observation and perfect mutual silence, written across 2.5 million light-years of empty space. We will never speak to Andromeda, but if anyone is there, they are looking back at us, seeing the same faint light, asking the same questions, reaching the same conclusions, and waiting, as we wait, for a merger that neither of us will live to see. Let us turn now to the gas that flows between Andromeda and the Milky Way, because even the empty space between the two galaxies is not entirely empty, and what fills it tells a remarkable story. For a long time, astronomers assumed the space between galaxies was almost perfectly void, a near-total vacuum with nothing in it at all. But more careful study has revealed that thin streams of hydrogen gas drift through the space between Andromeda and our own galaxy. These are the faint remnants of gas pulled out of the galaxies by gravitational interactions, or material left over from the formation of the local group billions of years ago. The gas is incredibly sparse, far thinner than the best vacuum we can create in a laboratory on Earth. But it is there, threading through the darkness, connecting the two galaxies with the faintest of bridges. As Andromeda and the Milky Way fall toward each other, this intergalactic gas will play its part in the eventual collision. When the galaxies finally meet, their gas, both the gas within them and the gas between them, will be compressed and stirred, fueling the burst of star formation that will light up the merger. So, even the seemingly empty gulf between the galaxies holds material that will one day contribute to the birth of new stars in the merged galaxy of the far future. Nothing in the cosmos is truly wasted. The thin gas between galaxies, the streams pulled from devoured dwarfs, the clouds within the spiral arms, all of it is part of the great cycle of cosmic material, endlessly drawn together, compressed, ignited into stars, and eventually scattered again. Andromeda is a participant in this cycle on a scale almost beyond comprehension, a galaxy that has been gathering, processing, and recycling cosmic material for billions of years, building its trillion stars from the raw hydrogen of the early universe and the enriched debris of countless stellar generations. Now let us think about how astronomers measure the motion of Andromeda, because knowing that it is approaching, and how fast, is itself a remarkable achievement. When light comes to us from a moving object, the motion subtly shifts the light's properties. If the object is moving away, its light is stretched toward longer, redder wavelengths. If the object is moving toward us, its light is compressed toward shorter, bluer wavelengths. By carefully analyzing the light from Andromeda, breaking it into its component colors, and measuring the precise positions of certain features in that spectrum, astronomers can determine whether the galaxy is approaching or receding, and how fast. When they did this for Andromeda, they found its light shifted toward the blue, revealing that the galaxy is approaching us. This was one of the first clues that Andromeda was bound to the Milky Way, rather than fleeing with the general expansion of the universe. But measuring the approach speed along our line of sight was only part of the puzzle. To predict whether Andromeda would actually collide with the Milky Way, astronomers needed to know its sideways motion too, whether it was heading straight for us or destined to drift past at an angle. Measuring such a tiny sideways motion across 2.5 million light-years is extraordinarily difficult. It requires detecting the minuscule shift in Andromeda's position over years of observation. A shift so small, it pushes the limits of even our finest telescopes. By comparing precise images taken years apart, astronomers were finally able to measure Andromeda's sideways motion, and they found that the galaxy is heading almost directly toward us. The collision, it turns out, will be close to head-on, ensuring that the two galaxies will indeed merge rather than merely brush past each other. This is a triumph of careful observation. The ability to measure the motion of an object 2.5 million light-years away, with enough precision to predict an event 4 billion years in the future. It speaks to how far our understanding of Andromeda has come, from the ancient observers who saw only a faint cloud, to modern astronomers who can chart the galaxy's trajectory across billions of years. Consider, too, the difference between how Andromeda appears and how it truly is, because the gap between appearance and reality is at the heart of understanding its scale. To the naked eye, on a dark night, Andromeda is a faint, dim oval, barely visible, easily mistaken for a smudge on the eye or a wisp of cloud. It gives no hint of its true nature. Nothing about its appearance suggests a galaxy of 1 trillion stars, larger than our own, surrounded by an invisible halo reaching across 1 million light-years. It looks like the most modest, unremarkable object imaginable. This is the great deception of cosmic distance. the most magnificent structures in the universe, viewed across the immense gulfs of space, are reduced to faint glimmers or rendered completely invisible. Andromeda, for all its grandeur, must compress its trillion suns into a single dim oval by the time its light reaches us. The reality is overwhelming. The appearance is underwhelming. And the only way to bridge that gap is through knowledge, through the painstaking work of astronomers who measured the distance, counted the stars, weighed the black hole, and revealed the true nature of the faint smudge. Without that knowledge, Andromeda is just a dim patch of light. With it, the same patch becomes a window into one of the grandest objects in the local universe, a galaxy of staggering scale, intimately bound to our own fate. This is perhaps the deepest lesson Andromeda teaches. The universe does not reveal its grandeur easily. Its greatest wonders are hidden behind veils of distance, dimmed to near invisibility, disguised as faint and unremarkable smudges. It takes effort, curiosity, and the slow accumulation of understanding to see past the appearance to the staggering reality beneath. The faint oval and the trillion-star giant are the same object, and the difference between them is entirely in what we know. Let us think about where Andromeda's light has traveled on its long journey to us, because the path it takes reveals the structure of the space between the galaxies. The light that left Andromeda 2.5 million years ago has spent almost its entire journey in the near-perfect emptiness of intergalactic space. It left the bright disk of Andromeda, passed through the galaxy's faint outer halo, and then entered the vast void between the galaxies, a realm of almost nothing, where the only company is the occasional drifting atom of hydrogen and the faint glow of distant galaxies. For most of its journey, the light traveled through this emptiness undisturbed, moving in a perfectly straight line across the gulf at the unchanging speed of light. Then, near the end of its journey, it entered the outer halo of our own Milky Way, passed through the disk of our galaxy, and finally reached the Earth, where it descended through our atmosphere and landed on the eye of an observer or the mirror of a telescope. That long, lonely journey, millions of years through near-total emptiness, bracketed by brief passages through the halos and disks of two galaxies, is the path that connects you to Andromeda. Every photon of Andromeda's light has made this voyage, traveling in silence through the dark for longer than humanity has existed, only to end its journey in the brief instant of being seen. There is something profound in considering the patience of light, how it travels for millions of years without rest, without change, carrying its ancient image faithfully across the void, until at last it arrives and delivers its message. The light does not age in the way we understand aging. It simply travels endlessly, at the unvarying speed that nothing can exceed, bridging the gulf between galaxies one photon at a time. When you see Andromeda, you are the recipient of one of the longest journeys in the universe, a voyage of light across 2.5 million light-years of emptiness, ending in the simple act of perception. Now, turn your attention to the discovery itself and how profoundly it reshaped the human story, because the moment Andromeda was understood was a turning point unlike any other in the history of science. For thousands of years, humans believed they lived in a small, contained cosmos. The ancient picture placed the Earth at the center, with the sun, moon, planets, and stars circling around it. Even after that picture was overturned, even after the Earth was demoted to a planet orbiting the sun, the prevailing belief held that our galaxy, the Milky Way, was the entirety of existence. The faint band of light arching across the night sky, the band we call the Milky Way, was understood to contain all the stars there were. Beyond it, people assumed, was simply nothing, the edge of everything. The fuzzy patches astronomers catalogued, the nebulae, were thought to be clouds of gas inside this single, all-encompassing galaxy. Andromeda was just one such patch, easily dismissed. There was a great debate among astronomers in the early 20th century about the true nature of these nebulae. One camp argued they were small, nearby objects within the Milky Way. The other camp argued, boldly, that they might be entire separate galaxies, island universes, as the phrase went, lying far beyond the bounds of our own. The debate could not be settled because no one could measure the distance to a nebula with any reliability. Without distance, there was no way to know whether Andromeda was a small cloud nearby or a vast galaxy impossibly far away. This is where the pulsing stars changed everything. When Edwin Hubble identified Cepheid variable stars within Andromeda and used their steady rhythm to calculate the distance, the debate ended in an instant. The distance he found was so enormous that Andromeda simply could not fit inside the Milky Way. It had to be a separate galaxy, lying far beyond our own. The island universe theory was correct. In a single measurement, the size of the known universe expanded almost beyond reckoning. The Milky Way went from being all of existence to being a single galaxy among countless others. Imagine the shift in perspective this required. For all of human history up to that point, our galaxy had been the whole universe. Suddenly, it was one of perhaps hundreds of billions. Our entire stellar home, with its hundreds of billions of stars, was revealed to be a single island in a sea so vast that the mind reeled trying to grasp it. This was one of the most profound expansions of human understanding ever achieved. It is comparable to the moment when humanity first realized the Earth was not the center of everything. And it began with Andromeda, that faint, easily overlooked smudge of light that turned out to be a galaxy of 1,000,000,000,000 suns. The discovery did not stop there. Once astronomers knew that Andromeda and the other nebulae were distant galaxies, they began measuring how those galaxies moved, and they found something even more startling. Almost every galaxy was moving away from us. The farther away a galaxy was, the faster it was receding. This was the discovery that the universe is expanding, that space itself is stretching, carrying galaxies apart from one another. It was the first solid evidence that the universe had a beginning, that it had been smaller and denser in the past, and that it had expanded outward from some initial state into the vast cosmos we see today. All of this flowed from the study of galaxies like Andromeda. The faint patch of light that ancient people called a little cloud became the key that unlocked our understanding of the universe's size, its history, and its ultimate fate. Andromeda is not just a galaxy. It is a milestone in human thought, the object that taught us how small we are, how vast the cosmos is, and how the entire universe is in motion, expanding outward from a beginning billions of years ago. But Andromeda is also special in another way, one that sets it apart from nearly every other galaxy in the universe. Recall that almost all galaxies are receding from us, carried away by the expansion of space. Andromeda is one of the rare exceptions. It is approaching. The reason for this exception is gravity. Andromeda and the Milky Way are close enough and massive enough that the gravitational attraction between them overwhelms the expansion of the universe in our local region. Within our local group of galaxies, the expansion of the universe does not hold sway. Gravity has won, binding the galaxies of the group together, holding them close while the rest of the universe streams away into the distance. This is why Andromeda is falling toward us while nearly everything else flees. It is bound to us, locked in a gravitational relationship that has been pulling the two galaxies together since the early universe. The expansion of space stretches the void between distant galaxy groups, but within a bound group like ours, gravity rules, and the galaxies move according to their mutual attraction. So as you watch Andromeda growing slowly larger across the eons, understand that you are witnessing one of the few places in the entire universe where gravity has defeated the cosmic expansion. A small island of galaxies holding together while the rest of creation drifts apart. In the deep future, when the expansion has carried all other galaxies beyond the reach of our telescopes, the merged remains of Andromeda and the Milky Way will still be here, bound together, the last great structure visible to whatever observers might remain. The expansion of the universe will eventually isolate our local group, leaving it alone in an ever-emptying void. But within that isolation, Andromeda and the Milky Way, by then merged into Milkomeda, will remain united, a single galaxy holding its stars close, while the rest of the cosmos vanishes into darkness. This is the long-term destiny, written into the gravity that now draws Andromeda toward us. Let us consider, too, what it would be like to actually travel to Andromeda, because the impossibility of such a journey reveals the scale of the distance more vividly than any number. The fastest spacecraft humanity has ever built travels at a tiny fraction of the speed of light. Even our swiftest probes, flung outward at tremendous velocity, would take tens of thousands of years just to reach the nearest star beyond our Sun, a star only about 4 light-years away. Andromeda is 2.5 million light-years away. To travel there with current technology would take not thousands of years, not millions of years, but a span of time so vast that it defies any practical meaning. Even if we could somehow build a ship that traveled at a meaningful fraction of the speed of light, a feat far beyond anything we can currently achieve, the journey would still consume tens of thousands of years, perhaps far more. No human civilization, no living being as we understand it, could survive such a voyage. Andromeda is, for all practical purposes, forever beyond our reach. We can see it, we can study it, we can measure it and understand it. But we can never go there. The distance is simply too great. The speeds required too far beyond our grasp. This is the cruel irony of the cosmos. The universe is filled with wonders, trillions of galaxies, countless worlds, sights beyond imagining, and yet nearly all of them are sealed away from us by distances that no traveler could ever cross. Andromeda, our nearest large neighbor, is already impossibly far. Everything beyond it is farther still. We are, in a sense, prisoners of our cosmic neighborhood, able to gaze out at the universe, but unable to touch more than the tiniest fraction of it. And yet, even within that limitation, there is wonder. We cannot travel to Andromeda, but Andromeda travels to us, falling toward us across the void, growing slowly larger in our sky, destined one day to merge with our home. We cannot send a ship across 2.5 million light-years, but light makes that journey constantly, carrying Andromeda's image to our eyes every clear night. In a way, Andromeda comes to us, even though we can never go to it. The light reaches across the gulf, the gravity pulls the galaxies together, and what we cannot achieve by travel, the cosmos achieves by its own slow, patient processes. Consider what astronomers have learned by comparing Andromeda to our own galaxy, because this comparison is one of the most valuable tools in all of astronomy. We can never see the Milky Way from the outside. We are trapped within its disk, surrounded by its stars, unable to step back and view the whole. Everything we know about our galaxy's overall shape, we have had to infer indirectly, by mapping the positions and motions of stars, by tracing the spiral arms from within, by studying the distribution of gas and dust. It is like trying to understand the shape of a vast city while standing in the middle of one of its streets, never able to rise above and see the whole layout from the air. Andromeda, however, we can see from the outside. It is tilted at an angle that reveals its spiral structure, its disk, its bulge, its arms. By studying Andromeda, we learn what our own galaxy must look like. Because the two galaxies are so similar in many ways, both large spirals, both with central bulges and sweeping arms, Andromeda serves as a kind of mirror, showing us the structure we cannot directly observe in our own home. When astronomers want to understand how a spiral galaxy is built, how its stars are distributed, how its arms wind outward, how its halo extends into space, Andromeda is often the galaxy they turn to, because it is close enough to study in extraordinary detail and similar enough to serve as a model for our own. In this sense, Andromeda has taught us about ourselves. By looking at our neighbor, we have learned to see our own galaxy more clearly. The faint oval in the sky is not just a distant object of curiosity. It is a window through which we glimpse the true nature of the Milky Way, the galaxy we live in but can never fully see. And the more closely astronomers examine Andromeda, the more detail emerges. Modern surveys have mapped its stars in numbers approaching the hundreds of millions, tracing the structure of its disk and halo with unprecedented precision. They have identified the streams of stars left behind by devoured galaxies, the clusters of ancient suns scattered through its halo, the regions of active star formation glowing within its arms. Each new observation adds a piece to the portrait, building an ever more detailed picture of this colossal neighbor, and, by extension, of our own galaxy. Andromeda is, in many ways, the best-studied large galaxy beyond our own, simply because it is the closest. Every advance in telescope technology brings new detail into view, new stars resolved, new structures mapped, new mysteries uncovered. And there are mysteries. For all that we have learned, Andromeda still holds secrets. The exact details of its history of mergers, the precise nature of its central double nucleus, the full extent and composition of its dark matter halo, the question of whether life exists anywhere among its trillion stars, these remain open questions, puzzles that future generations of astronomers will continue to probe. Andromeda is not a solved problem. It is an ongoing story, a galaxy we understand better with each passing year, but have not yet fully comprehended. This too is part of its scale, not just the scale of its size, but the scale of its mystery, the sheer depth of what remains to be learned about a single galaxy among billions. Let us widen our view and place Andromeda within the full hierarchy of cosmic structure, because understanding where it sits in the grand scheme deepens our sense of its scale. A planet orbits a star. A star, with its planets, is one of hundreds of billions in a galaxy. A galaxy, like Andromeda, is one of dozens in a group. A group, like our local group, is one of many in a larger structure. And those larger structures are themselves part of even greater assemblies, stretching outward to the limits of the observable universe. Andromeda and the Milky Way, with their small companion galaxies, make up the local group, a gathering of more than 50 galaxies bound together by gravity, dominated by the two great spirals. This group spans several million light-years across, with Andromeda and the Milky Way at its two great anchors, and the dwarf galaxies scattered around and between them. The local group is not isolated. It sits at the edge of a much larger structure, a great collection of galaxy groups and clusters bound together across a region tens of millions of light-years wide. And that structure, in turn, is part of an even grander assembly, a vast collection of galaxy clusters spanning hundreds of millions of light-years, threaded through the cosmic web. At each level of this hierarchy, the scale multiplies, the numbers growing until they lose all meaning. 1 trillion stars in Andromeda, dozens of galaxies in the local group. Thousands of galaxies in the larger structures. Hundreds of billions, perhaps trillions, of galaxies in the observable universe as a whole. Andromeda, for all its staggering size, is a single point in this immense hierarchy. One galaxy among an almost limitless multitude. And yet, it is our galaxy's nearest great companion, the closest of all the major galaxies, the one we know best and the one most intimately tied to our own fate. In the vast cosmic hierarchy, Andromeda occupies the place right beside us, our partner in the local group, our future merger companion, our nearest neighbor among the trillions of galaxies scattered across the universe. To understand Andromeda's scale is to understand this dual nature. On one hand, it is colossal, 1 trillion suns, larger than the Milky Way, surrounded by an invisible halo of immense extent. On the other hand, it is tiny, a single galaxy among trillions, a single point in a cosmic web of unimaginable size, dwarfed utterly by the larger structures that contain it. Both things are true at once. Andromeda is both a giant and a speck, depending on the scale at which you view it. This is the dizzying nature of cosmic scale, that an object can be at once unfathomably large and vanishingly small, 1 trillion-star galaxy that is nonetheless just one tiny island in an ocean without visible shores. Now let us reflect on the deep age of Andromeda, because the galaxy is not merely vast in space but ancient in time, formed in the early ages of the cosmos. Andromeda, like the Milky Way, began to form billions of years ago, in the era after the universe's first stars and galaxies appeared. In those early ages, the universe was a very different place. Denser, hotter, richer, with the gas from which galaxies form. Small clumps of matter drew together under gravity, merging and growing, gradually assembling into the great spiral galaxy we see today. Over billions of years, Andromeda built itself up, swallowing smaller galaxies, forming generation after generation of stars, slowly accumulating the trillion suns it now holds. The oldest stars in Andromeda are nearly as old as the universe itself, ancient suns that formed in the galaxy's earliest days and have been burning, in some cases, for the better part of the universe's entire history. These ancient stars are found mostly in the galaxy's halo and central bulge, the oldest regions of the galaxy, where the first stars formed long ago. The disk and spiral arms, by contrast, contain younger stars, born more recently from the galaxy's ongoing star formation. By studying the ages of Andromeda's stars, astronomers can read the galaxy's history, tracing when it formed, when it merged with other galaxies, when its bursts of star formation occurred. The galaxy is, in this sense, a living record of cosmic history, its stars a kind of archive, each generation marking a different epoch in the long story of Andromeda's growth. To look at Andromeda is to look not only across space but across time, to see a galaxy that has been assembling itself for billions of years, that contains stars older than almost anything else in the universe, that carries within it the full sweep of cosmic history written in the ages of its suns. And all of this, the billions of years of formation, the countless merged galaxies, the generations of stars, is contained within the faint oval that you can see with your own eyes on a dark night. The smudge of light is not just vast in size. It is vast in age, vast in history, vast in the depth of time it represents. It is one of the oldest, largest structures visible to the unaided human eye, a galaxy that has been growing since the early universe, that will continue until it merges with our own, and that holds within it a record of cosmic time stretching back almost to the beginning. Let us consider one more aspect of Andromeda's scale, the energy it produces, the sheer output of a trillion stars shining together. Each star in Andromeda produces energy through fusion, converting matter into light and radiation in its core. Our Sun alone produces an enormous amount of energy every second, more than human civilization has used in its entire history. Released in a single moment, over and over, second after second, for billions of years. Now multiply that by 1 trillion. The total energy output of Andromeda, the combined radiance of all its stars shining at once, is almost beyond the power of numbers to express. The galaxy pours out light in unimaginable quantities every second, in all directions, a flood of radiation streaming into space across the entire spectrum, from radio waves to visible light to high-energy radiation. A tiny fraction of that flood, after traveling for 2.5 million years, reaches the Earth, just enough to register as a faint oval in our sky. The overwhelming majority of Andromeda's light streams off in other directions, into the depths of the universe, reaching other galaxies, other worlds, other observers if any exist. The light we see is the merest sliver of the galaxy's total output, a single thin beam from a beacon shining in every direction with the power of 1 trillion suns. This is the engine of Andromeda, a galaxy-spanning furnace of fusion, converting matter into energy on a scale that dwarfs everything in human experience, shining steadily across billions of years, illuminating the cosmos with the combined light of its trillion stars. And it will continue to shine for billions of years more, even as it merges with the Milky Way, even as its spiral form dissolves into the great elliptical galaxy of the far future. The stars will keep burning, keep producing energy, keep shining into the void, long after every human concern has faded into the deep past. Andromeda is, in the truest sense, a powerhouse of the cosmos, one of the great engines of light in our corner of the universe, and the nearest such engine to our own. Let us return once more to the night sky, and to the simple act of looking. When you find Andromeda, that faint oval near the constellation that bears its name, you are performing an act that connects you to the entire history of astronomy. You are seeing what ancient observers saw and called a little cloud. You are seeing what early astronomers debated, unsure whether it lay inside our galaxy or far beyond. You are seeing what Edwin Hubble resolved into individual stars, proving it to be a separate galaxy and expanding the known universe 1,000-fold. You are seeing the object that helped reveal the expansion of the universe and the existence of countless galaxies beyond our own. And you are seeing it with your own eyes, directly. The ancient light landing on your retina after a journey of 2.5 million years. There is something deeply moving in that simple act. With nothing more than your eyes and a dark sky, you can reach across 2.5 million light-years and touch the light of 1 trillion suns. No instrument is required, just patience, a clear night, and the knowledge of where to look. The most distant object visible to the unaided human eye is a galaxy larger than our own, and you can find it tonight if the sky is dark enough. Think of all the beings throughout history who have looked at that same faint smudge, the ancient astronomers who first noted it, the medieval observers who recorded it, the astronomers of the last century who finally understood it. And now you, holding in your mind a fuller understanding than any of them, knowing the distance, the size, the trillion stars, the central black hole, the dark matter, the coming collision, the place within the cosmic web. The same faint light has fallen on all those eyes across the centuries, but only in recent times have we truly understood what we were seeing. You stand at the end of that long chain of human curiosity, looking at the same patch of light that puzzled our ancestors, but armed with knowledge they could only dream of. That is a kind of privilege. To live in an age when the true nature of Andromeda is known, when the faint smudge has been revealed as the colossal galaxy it truly is. Let us think carefully about what the collision will mean for the individual stars, because the fate of a single sun in such an event reveals the strangeness of galactic scale. When two galaxies merge, the stars do not collide. This is worth repeating, because it runs so strongly against intuition. The space between stars is so vast that even when two galaxies pass completely through each other, the chance of any two stars striking one another is almost nothing. Picture our Sun, with the Earth and the other planets orbiting it. The nearest star to our Sun is light years away, an enormous distance, far greater than the size of our entire solar system. When Andromeda sweeps through the Milky Way, the stars of both galaxies will glide past one another across these vast gaps, almost never coming close enough to interact directly. What will change is the gravitational environment. As the galaxies merge, the gravity of all those stars will mix and shift, and individual stars will find their orbits altered. Some will be flung outward, cast into long looping paths far from the galactic center. Some will be drawn inward. Some may be ejected entirely, hurled out of the galaxy altogether to wander the intergalactic void alone. Our own Sun, if it still existed at the time of the merger, might experience any of these fates. It might be tossed into the outer reaches of the new galaxy, or pulled toward the center, or flung into the dark between galaxies, but it would not be destroyed by collision, because the chance of striking another star is so vanishingly small. This is the strange gentleness of galactic mergers. Despite the violence implied by the word collision, the stars themselves mostly survive untouched, simply rearranged into new orbits within the merged galaxy. The drama is gravitational, not physical, a reshaping of orbits rather than a smashing of stars. The spiral arms unravel, the disks dissolve, the galaxies lose their shapes, and yet the individual stars, for the most part, sail on serenely through the chaos, their courses bent by gravity but their substance intact. This is what scale does. It turns what should be a catastrophe into a slow, almost stately rearrangement. Two galaxies of hundreds of billions and a trillion stars passing through each other with hardly a single direct impact. The immense emptiness between the stars protecting each one from its neighbors. Now imagine standing on a world that survives this merger, watching the night sky over the hundreds of millions of years the process takes. At first, Andromeda would loom enormous in the sky, its spiral arms stretched and distorted by the approaching gravity. Then, as the galaxies passed through each other, the sky would fill with the glow of newborn stars igniting in the compressed gas, brilliant blue points flaring into existence across the heavens. The two galactic cores would blaze, their supermassive black holes drawing material inward and shining with the radiation of that infalling matter. Over time, the familiar patterns of the night sky would dissolve, the constellations distorted beyond recognition as stars shifted into new positions. The luminous band of the Milky Way, the river of light we see arching across our sky, would warp and twist as the disk of our galaxy was torn apart by the merger. And eventually, over hundreds of millions of years, the chaos would settle. The merged galaxy would take its new form, a vast elliptical swarm of stars, smooth and rounded, with no spiral arms, no disk, just a great rounded glow of countless suns. The night sky of that distant future would look utterly different from ours. No band of the Milky Way, no familiar constellations, just the scattered light of the merged galaxy's stars, and, beyond them, the darkness of an ever-expanding universe with fewer and fewer distant galaxies visible. No human will witness this transformation. It lies billions of years in the future, far beyond the lifespan of our species, far beyond even the habitable lifetime of the Earth. But it is coming, written into the gravity that now draws Andromeda toward us, as certain as anything in the cosmos can be. The faint smudge in our sky tonight is the early act of a drama that will unfold over billions of years, ending in the union of two great galaxies and the birth of a new one. Let us also dwell on the humility that Andromeda imposes, because contemplating it changes how we see ourselves. Andromeda teaches us, more directly than almost anything else in the sky, just how small we are. Here is a galaxy of 1 trillion stars, larger than our own, and it is merely the nearest of trillions. Here is an object so vast that light takes 200,000 years to cross it, so distant that its light takes 2.5 million years to reach us. And on the cosmic map, it counts as our next-door neighbor. Against such scales, the entire span of human history shrinks to nothing. Every empire, every civilization, every life that has ever been lived, occupies a sliver of time so brief that Andromeda has not visibly changed across all of it. The galaxy that hung in the sky over the first humans is the same galaxy that hangs in the sky tonight, unchanged, on human timescales, by everything we have done. And yet, there is a strange dignity in this smallness. For all our insignificance against the scale of Andromeda, we are the ones who figured out what it is. We are the ones who measured its distance, counted its stars, weighed its black hole, predicted its collision with our own. A species confined to a single small planet, with brief lifespans and limited senses, has nonetheless reached out across 2.5 million light-years to understand a galaxy of 1 trillion suns. That achievement does not erase our smallness, but it transforms it. We may be tiny, but we are tiny things that understand the cosmos. Tiny things that look up at a faint smudge of light and comprehend its true nature. Andromeda humbles us with its scale and elevates us with the fact that we can grasp that scale at all. This is the paradox at the heart of contemplating the cosmos. The universe is vast beyond comprehension, and we are smaller than we can easily accept. And yet the same minds that feel that smallness are the minds that measured the universe, that found the galaxies, that understood Andromeda. We are dust that contemplates the stars. We are specks that have charted the cosmos. And Andromeda, the faint oval in our sky, is one of the grandest objects we have ever come to understand. 1 trillion suns, falling slowly toward us, revealed in all its true scale by the curiosity of a small and fragile species on a single distant world. Let us spend a final moment imagining the merger itself, in the full sweep of its grandeur, because it is the culmination of everything Andromeda is. 4 billion years from now, the two galaxies will make their first close pass. Andromeda, by then, a vast presence filling a huge portion of the sky, will sweep through and past the Milky Way, the two great spirals interpenetrating without their stars ever colliding. Gravity will seize both galaxies, drawing out long tidal tails of stars, immense streamers flung into the dark, glowing arcs reaching across hundreds of thousands of light-years. The gas clouds will slam together, igniting a storm of new star formation, the sky lighting up with the fierce blue glow of newborn suns blazing into existence by the millions. Then the two galaxies will separate, pulled apart by their momentum, only to be drawn back together by gravity, returning for a second pass and a third. With each encounter, their structures will unravel further, their elegant spirals dissolving into chaos. Over hundreds of millions of years, the dance will tighten, the two galaxies winding closer and closer, until at last they can no longer pull apart. They will settle together, their stars mingling into a single vast swarm, their separate identities gone forever. In place of two spirals, there will be one enormous elliptical galaxy, smooth, rounded, featureless, a great ball of countless stars with no arms and no disk. Milky will be born. At its center, the two supermassive black holes will have merged into one, a single titanic engine of gravity ruling the heart of the combined galaxy. The star formation triggered by the merger will eventually fade, the gas exhausted, and Milky will settle into a long, slow old age, a galaxy of aging stars drifting in an increasingly empty universe. For the expansion of the cosmos continues, carrying other galaxies ever farther away. In the far future, after the merger, the descendants of our galaxy will look out into a sky growing emptier with time, the distant galaxies receding beyond the reach of sight, until Milky hangs alone in a darkening void. But that is the distant future, billions upon billions of years away. For now, Andromeda is still a separate galaxy, a distinct spiral, falling toward us across the dark, its light reaching our eyes after a journey of 2.5 million years. For now, we can still see it as it is, a magnificent wheel of stars, our nearest great neighbor, our future companion, our mirror in the sky. Consider, for a moment, the act of measuring Andromeda's size, because the very fact that we can assign it a number is itself a triumph worth pausing on. When astronomers say Andromeda spans roughly 200,000 light-years, they are describing the extent of its bright, visible disk, the region where the stars are dense enough to shine clearly across the gulf of intergalactic space. But the galaxy does not end at a sharp edge. It fades gradually, the stars thinning out toward the rim, the bright disk giving way to the faint outer regions, and then to the even fainter halo beyond. There is no clean boundary, no line where the galaxy stops and empty space begins. Instead, Andromeda trails off into the dark, growing dimmer and dimmer until it can no longer be distinguished from the blackness around it. This makes measuring its true size a subtle challenge. Where do you draw the line? If you measure only the bright disk, you get one number, around 200,000 light-years. If you include the faint outer regions, the number grows. And if you include the vast, diffuse halo of stars and dark matter that surrounds the galaxy, the number becomes enormous, reaching well over 1 million light-years across. The size of Andromeda, in other words, depends on how you define its edge. This is true of all galaxies. They do not have hard boundaries. They are concentrations of stars and matter that grow gradually thinner with distance from the center, fading imperceptibly into the surrounding space. The faint smudge we see with the naked eye is only the bright core. The full extent of the galaxy, including its faint halo, reaches far beyond what any eye or ordinary telescope can detect, traced only by the most sensitive instruments capable of picking out the rare, scattered stars of the outer halo. When astronomers mapped Andromeda's halo by detecting these faint, distant stars, they discovered that the galaxy's true extent was far greater than the visible disk, suggested that Andromeda reaches outward across a region so vast that it nearly touches our own galaxy's halo. This is why we say the two galaxies' outer envelopes are already brushing against each other. The bright disks are separated by 2.5 million light-years, but the faint halos extend so far that the gap between them is already partly bridged. In a sense, Andromeda and the Milky Way are not entirely separate objects anymore. Their outermost reaches have begun to overlap, the first faint contact in a merger that will not fully unfold for billions of years. So the question, how big is Andromeda, does not have a single answer. It is 200,000 light-years if you mean the bright disk. It is over 1 million light-years if you mean the full halo. And by the deepest measure, the reach of its gravitational influence, the extent of its dark matter, it is so large that it already touches our own galaxy across the void. This is the final, subtlest lesson of Andromeda's scale. Even the size of a single galaxy is not a simple fact, but a question of definition. A number that grows the more carefully you look, until the boundaries blur and you realize that the galaxy reaches farther than any clean edge could capture. Andromeda is bigger than it looks, bigger than its bright disk, bigger than its faint halo, as big, in the end, as the reach of its gravity, which extends across the void to meet our own. And that reach is what will, in time, draw the two galaxies together. The gravitational embrace that has already begun, written into the faint overlap of their halos, building toward the great merger of the distant future. There is one more dimension of Andromeda worth exploring, the way it connects the very small to the very large. The way a single galaxy ties together everything from individual atoms to the structure of the universe itself. Within Andromeda, every star is a furnace where the simplest atoms are fused into heavier ones. Hydrogen, the most basic element, is transformed into helium, and in the most massive stars, into carbon, oxygen, and the heavier elements beyond. When those massive stars reach their ends and explode, they forge still heavier elements and scatter them across the galaxy. This means that Andromeda is not just a collection of stars. It is a vast machine for building the elements, a galaxy-spanning factory that has been transforming simple matter into complex matter for billions of years. The same process happened in our own galaxy, and it is why the Earth, and everything on it, is made of elements heavier than hydrogen. The atoms in your body were forged in stars, stars that lived and ended long before our sun formed. And the same is true for any planets that might exist in Andromeda. The rocky worlds of that distant galaxy, if they exist, are built from elements cooked in the hearts of Andromeda's stars, scattered by Andromeda's stellar explosions, gathered into new worlds over billions of years. So Andromeda connects the smallest scales, individual atoms, the fusion reactions in stellar cores, to the largest scales, the structure of the galaxy, its place in the cosmic web, its eventual merger with our own. It is a bridge across the full range of cosmic scale, from the subatomic to the galactic, all bound together in a single magnificent structure. When you look at the faint oval in the sky, you are seeing the combined result of countless fusion reactions in a trillion stellar cores, the accumulated work of billions of years of element building, the gathered light of a galaxy that has been transforming matter and shaping itself since the early universe. The smudge of light is the visible expression of processes operating at every scale, from the fusion of single atomic nuclei to the gravitational assembly of an entire galaxy. This is the true scale of Andromeda, not just its size in light years, not just its trillion stars, but the full span of processes it embodies, from the smallest particles to the largest structures, from the deepest past to the distant future. It is a single object that touches every level of cosmic reality. A galaxy that connects the atoms in your body to the structure of the universe. A faint smudge of light that contains within it the whole story of how matter organizes itself across the cosmos. And it is our nearest great neighbor, the closest such marvel to our own home, the one we can study in the most detail, the one whose fate is most intimately tied to ours. Let us end by returning to the simplest fact of all, the fact with which this journey began. When you look at Andromeda, you are seeing light that left it 2.5 million years ago. That light has traveled across the void for longer than humanity has existed, crossing 2.5 million light-years of near-perfect emptiness, to arrive at this exact moment, on your eye or your telescope. It is the oldest light you can see with your unaided eyes, older than our species, older than human history by a factor too large to grasp. and it comes from the largest, most distant object visible without a telescope, a galaxy of 1 trillion suns, larger than our own, falling slowly toward us across the dark. Everything about Andromeda stretches the limits of comprehension. Its distance, measured in millions of light-years, its size, measured in hundreds of thousands of light-years across, its population, measured in trillions of stars, its central black hole, measured in hundreds of millions of solar masses, its dark matter halo, reaching across 1 million light-years toward our own, its history, stretching back billions of years to the early universe, its future, culminating in a collision with the Milky Way 4 billion years from now. All of it, contained within a faint oval that you could cover with the tip of your finger held at arm's length. That is the true scale of Andromeda. A scale so vast that the mind cannot hold it, compressed by distance into a smudge so faint that most people will never notice it. But you have noticed it now. You know what it is. And the next time you stand beneath a dark sky and find that faint patch of light near the constellation that bears its name, you will see it differently. You will see not a smudge, but a galaxy. Not a cloud, but 1 trillion suns. Not a distant curiosity, but our nearest great neighbor, our future companion, our mirror in the sky, falling slowly toward us across an ocean of emptiness, carrying its ancient light to your eyes, connecting you across 2.5 million light-years to one of the grandest objects in the cosmos. And so we end where we began, with a faint patch of light and a long journey of photons through the dark. 2.5 million years ago, that light left a galaxy of 1 trillion suns. Tonight, it reaches you. Consider one last time the journey of that light. It began 2.5 million years ago, leaving a galaxy of 1 trillion suns. It crossed the emptiness between galaxies for longer than our species has walked the Earth. It passed through the dark, untouched, faithful, carrying its ancient image across the void. And tonight, after that immense voyage, it ends, on your eye, in your mind, becoming a faint patch of light that you now understand for what it truly is. You are the destination of one of the longest journeys in the cosmos. You are where Andromeda's light, after 2.5 million years, finally arrives, and now you know what it truly is. A galaxy of 1 trillion suns, larger than our own, falling toward us across the dark, carrying light older than humanity to your eyes on this night, in this moment. The next clear night, look up and find it. That faint patch of light is not small. It only looks that way from here. It is the true scale of Andromeda, and a glimpse of just how vast and how wondrous the universe we live in truly is.